Duffs Bridge and Marlee Bridge replacements. A case study in successful infrastructure development, the replacement of Duffs and Marlee bridges over Dingo Creek, located north of Wingham, marks a significant achievement in the Greater Terry City Council's efforts to upgrade aging infrastructure. Originally constructed in 1900 and 1926 respectively, these single-lane timber truss bridges served rural communities for over a century. However, by the early 21st century, the need for costly maintenance, due to the high-quality timbers and specialized labor required, made their upkeep unsustainable. As a result, the council undertook a major project to replace the two remaining timber truss bridges with modern, durable concrete structures, improving safety, functionality, and economic viability for the region. Both bridges had significant historical value, symbolizing the importance of rural connectivity in the early 1900s. The original openings were celebrated events, reflecting the crucial role these bridges played in linking agricultural communities. However, by 2003, load limits were imposed on both bridges due to structural concerns, which were further reduced in 2008. The restrictions on heavy vehicles caused disruptions for local businesses, dairy farmers, and travelers, leading to strong community advocacy for upgrades. The decision to replace the bridges was driven by the limitations of timber truss structures, which had become increasingly difficult and expensive to maintain. The Greater Terry City Council's proposal to construct two new concrete bridges aimed to provide the local community with reliable and safe infrastructure. With funding set aside over 2 years and a $2.5 million grant secured, the council initially estimated a project cost of $5 million. However, the first round of tenders revealed a significantly higher cost of over $9 million, leading the council to reject all tenders and reevaluate the project. To manage the complex task of replacing the two bridges, the council engaged GHD, a consulting firm, to oversee the investigation, design, demolition, and construction phases. GHD laid out an ambitious 2-year program targeting completion in April 2013 with a revised estimated cost of $6.9 million. The decision to build Duffs Bridge first allowed Boer Road to facilitate the construction of Marlee Bridge, thus avoiding the narrow, winding detour that would have complicated logistics for equipment deliveries. During the options analysis in 2011, the project team focused on 3 key criteria: cost, functionality, and traffic impact. A 3-span, 2-lane design was chosen for both bridges, offering significant cost savings and reducing traffic disruptions. The decision to construct Marlee Bridge on its existing alignment saved an estimated $1.4 million in approach road works, but required temporary road closures. Unexpected discoveries during the design phase, the presence of indigenous artifacts at the planned downstream alignment for Duffs Bridge prompted a realignment to the existing bridge's location. This adjustment minimized environmental impact and avoided significant delays and costs. To maintain the project's budget and timeline, the engineering team developed nearly identical bridge designs for Duffs and Marlee, accommodating site-specific constraints while streamlining construction processes. Regional geotechnical solutions recommended using large-diameter, permanently cased board piles for the bridge foundations, penetrating 3 meters into the bedrock. This approach addressed potential scour issues in the fast-flowing Dingo Creek and eliminated the need to drill through the existing timber decks, enhancing worker safety. Steel-encased concrete piles were extended up to the headstock level, further improving stability. Demolition of the old timber truss bridges required careful planning due to the unpredictable behavior of aging timber structures. For Duffs Bridge, which stood over 16 meters high, a licensed demolition company used a 500-ton crane to safely dismantle the structure. The bridge was closed to traffic during the demolition, and each span was lifted and lowered to the ground for disassembly, minimizing the time workers spent at height. At Marlee Bridge, improvements in the demolition process were implemented based based on lessons learned from Duffs. The construction team used a temporary support structure under the timber span, providing a stable work platform and reducing crane standby time. By using identical steel support structures for both bridges, the project achieved cost efficiencies and minimized risks during demolition. Precast concrete components played a crucial role in reducing construction time and costs. The use of pre-stressed concrete planks with transverse post-tensioning eliminated the need for an in-situ concrete deck, allowing immediate use of the new bridges and significantly reducing road closure durations. The approach also enhanced safety, as edge planks with attached scaffolding provided instant protection for workers at height. A key challenge in using pre-cast planks was ensuring durability and protection against corrosion. The project adopted a divided DSI system, which involved pre-routed transverse bars encased in a corrugated PVC sheath for double corrosion protection. This solution not only simplified construction, but also provided long-term resilience against water infiltration. Continuous improvement and project outcomes throughout the project, the construction team demonstrated a commitment to continuous improvement. Time-lapse photography and careful site planning allowed for the identification of critical path activities and the implementation of lessons learned from Duffs Bridge at Marlee. The team achieved greater efficiencies, such as reducing crane standby times and optimizing precast production schedules. The project concluded with the successful opening of Duffs Bridge in November 2012, 5 months ahead of schedule, and Marlee Bridge in April 2013, within the planned 10-day road closure. Despite challenges such as flooding in early 2013, the project was completed on time and within budget, demonstrating the value of innovative project management and adaptive strategies. The replacement of Duffs and Marlee bridges has delivered long-term benefits to the greater Terry community. The new concrete structures support higher load capacities, enhancing safety and economic growth in the region by accommodating 44-ton trucks and 68-ton B-doubles. The wider two-lane design has improved traffic flow, and the use of durable materials ensures minimal maintenance in the future. Moreover, the project set a precedent for future bridge replacements by the Council, showcasing the effectiveness of leveraging innovative solutions and adaptive project management. The temporary steel support structure used during construction was designed for potential future use as an emergency bridge, reflecting a sustainable approach to infrastructure development. The Duffs and Marlee bridge replacements exemplify how careful planning, continuous improvement, and engineering ingenuity can overcome challenges and deliver high-quality infrastructure. The project has not only met the immediate needs of the community, but also laid the groundwork for sustainable and resilient infrastructure in the future. Bridge. Construction of an FRP composite bridge, the Bridge project marks a significant advancement in bridge engineering with the construction of Poland's first road bridge made entirely of fiber-reinforced polymer, FRP composites. Completed in 2015 by Mostostal Warszawa, this bridge is not just a first for Poland, but also holds the distinction of having the longest span for a bridge of its kind in the world. Utilizing FRP technology represents a new era in civil engineering, offering innovative solutions for both new construction and strengthening existing infrastructure. The technology's unique properties, such as corrosion resistance, low thermal conductivity, and electromagnetic transparency, set it apart from traditional materials like steel, presenting both opportunities and challenges. Fiber-reinforced polymer, FRP, is a composite material that consists of fibers, such as carbon, glass, aramid, or basalt, embedded within a polymer matrix. These fibers, making up between 30% and 70% of the composite volume and roughly 50% of its weight, are responsible for providing strength, stiffness, and other essential structural characteristics. The polymer matrix acts as a binder, maintaining the position of of the fibers, distributing loads among them and protecting them from environmental damage and mechanical wear. Together, the fibers and matrix form an anisotropic material, meaning its mechanical properties vary depending on the fiber type, alignment, volume, and matrix quality. In civil engineering, different types of FRP are commonly used. Carbon fiber reinforced polymer, CFRP, known for its high strength-to-weight ratio and rigidity. Glass fiber reinforced polymer, GFRP, offers a cost-effective option with good tensile strength. Aramid fiber reinforced polymer, AFRP, notable for high impact resistance and energy absorption. Basalt fiber reinforced polymer, BFRP, exhibits good thermal resistance and cost efficiency. Advantages of using FRP composites in bridge construction. One of the main advantages of using FRP composites for bridges is their resistance to corrosion, particularly when exposed to harsh environmental conditions such as marine environments or areas where de-icing salts are used. Unlike traditional steel reinforcement, which is susceptible to chloride-induced corrosion, FRP composites maintain their structural integrity, thereby extending the service life of the bridge. FRP materials also exhibit excellent dimensional stability, low thermal conductivity, and electromagnetic transparency, making them suitable for applications where these properties are crucial. For example, in environments where thermal variations are significant, the low thermal conductivity of FRP helps in maintaining structural stability. Additionally, because FRP does not conduct electricity, it is ideal for use in locations where electromagnetic interference is a concern. Another significant benefit is the lightweight nature of FRP composites, which reduces the load on the foundation and supports. This characteristic allows for easier and faster installation compared to conventional materials. The low life cycle costs associated with minimal maintenance further enhance its appeal, making FRP a cost-effective option in the long term despite its higher initial costs. The challenges and limitations of FRP composites, while the advantages of FRP composites make them an attractive option for bridge construction, they do have limitations that must be addressed. The primary drawback is the high initial cost, which can be a deterrent for budget-constrained projects. Furthermore, FRP materials are prone to mechanical damage and have poor fire resistance compared to traditional materials like steel and concrete. Their lower shear strength and limited strain to failure mean that careful consideration and specialized design guidelines are required to use them effectively in structural applications. Another challenge is that FRP composites cannot be bent or reshaped in the field as steel can, which limits their flexibility during installation. The longer load transfer lengths required when using FRP materials can complicate design and construction processes. Additionally, due to differences in thermal compatibility between concrete and FRP, thermal stresses could arise under varying temperature conditions, necessitating unique engineering solutions. The Bridge Project, a case study. The Bridge Project, an innovative road bridge made of FRP composites, stands as a testament to the potential of FRP technology in modern infrastructure. Completed in 2015, this bridge became Poland's first road bridge built entirely using FRP composites, showcasing the feasibility of using advanced materials in large-scale civil engineering projects. The choice of FRP for the bridge was driven by the need for a durable, corrosion-resistant solution that could withstand the environmental conditions of the site while offering a long service life with minimal maintenance. In conventional bridge construction, steel reinforcement is prone to corrosion, especially in environments where chloride exposure is prevalent. Studies of bridge failures in Germany have shown that 2/3 of the recorded failures were due to reinforcement corrosion caused by chlorides. By using FRP composites, the bridge eliminates this common problem, promising a much longer service life. The mechanical behavior of FRP materials differs significantly from that of steel, as FRP composites are anisotropic. The properties of the material depend on the type of fibers used, e.g., carbon, glass, aramid, basalt, their volume fraction, and alignment within the polymer matrix. For example, carbon fibers provide high tensile strength and stiffness, while glass fibers are more flexible but less strong. This variability in material properties necessitates tailored design guidelines to ensure the safe and efficient use of FRP composites in bridge construction. The Composite's design had to account for these differences, incorporating innovative engineering solutions to accommodate the lower shear strength and different load transfer characteristics of FRP materials. The bridge's structural components, such as decks and supports, were fabricated using pultruded FRP profiles and pre-stressed CFRP strands. These components offered the necessary strength while minimizing the overall weight of the structure, enabling faster and more efficient construction. The Com Bridge project represents a milestone in the application of FRP composites for bridge construction, demonstrating the viability of this technology for creating durable and low-maintenance infrastructure. By addressing the challenges of corrosion, weight, and long-term maintenance costs, FRP composites offer a promising alternative to traditional materials, especially in environments where corrosion is a major concern. However, to fully realize the potential of FRP technology in civil engineering, it is essential to develop comprehensive guidelines for the design and construction of FRP-reinforced structures. The experience gained from projects like the Com Bridge provides valuable insights that can be applied to future developments, paving the way for broader adoption of FRP composites in bridge construction worldwide. The construction of the high-speed train viaduct on the Madrid-Galicia line represents a significant engineering achievement by Tecozam in collaboration with Ideas 3. The project involves the building of a crucial viaduct segment located in the Prado Cerdadello section, situated in Os Portos, Orense. This section is part of the broader high-speed rail initiative aimed at improving connectivity between Madrid and Galicia, facilitating faster travel, and enhancing transportation infrastructure across Spain. To execute this complex engineering task, the project employs advanced construction techniques and systems. The VGT 100 deck formwork system plays a critical role in shaping the viaduct's deck structure, providing the necessary support for concrete placement and ensuring the stability of the bridge during construction. This formwork system allows for precise molding of the deck, which is essential for achieving the required structural integrity and alignment. Complementing the formwork system, the County Route 24 truss system is utilized to provide additional support during the construction process. With its 24-meter span, this truss system facilitates the assembly and stabilization of large sections of the viaduct, enabling efficient construction across challenging terrains. The use of long-span trusses reduces the need for temporary supports, accelerating the construction process and minimizing disruptions to the surrounding environment.